Okay, so today we're going to talk, talk about solids, and remember that solids are going to have very strong intermolecular forces because they're closely packed together, and there's a lot of energy in those intermolecular forces. They're also restricted in what kind of motion they can undergo. So remember, they can really only vibrate between the atoms. So there's two types of solid states, and once we know what those are, then we have 5 types of solids that have various properties. We're going to look at something called the unit cell, and we're also going to figure out how many atoms are in each of the unit cells that we'll study. We need to know the coordination number of each cell, and then we'll just look briefly at how these things get packed. So the solid state, there's 2 possible solid states. One of them is the crystalline solid, okay, and that has a well-defined shape, and the particles are closely arranged. Compared to that to an amorphous solid, then doesn't have good orderly arrangements. It's more compact. More illy defined. So, for example, here is quartz, and you can see the pretty crystal kind of a form that it takes when it's packed in an orderly fashion. And here's the same thing, some more quartz, only this time it's not so nicely packed. Okay, it's more of an amorphous type of substance. Now, among crystals, okay, with crystal solids, we're going to study the atomic, molecular, ionic, metallic, and the network covalent. Okay, so let's just go ahead and get started looking at those. So, for example, this is our atomic structure. Now, in order to have an atom that can be formed into a solid, you really have to have a noble gas, and it has to be very, very cold. Okay, the only thing that holds those together are dispersion forces, because the only thing that's going on is the atoms have electrons that are moving around, and so that's how the dispersion forces happen. So this is really only for noble gases, because these are atomic structures. Now, these, I guess I didn't label these molecular structures. Molecular structures are caused by bonding in a covalent type of arrangement. Now, remember, covalents share electrons. They form these bonds, and they can have all kinds of forces that are important to them. They can have dispersion forces, so if they're really nonpolar, they stick together pretty strongly because there's nothing except dispersion in them. But that makes for, they're very weak individually, but when there are a lot of them, then they become more and more strong. You could also have some kind of a dipole-dipole situation, and there's also hydrogen bonding in those solids sometimes. This particular one, I think, was, I think this is an NH. I can't remember what this was. Maybe it's, I know, it was a CH4. That's really small. Again, for methane to be cold, it'd have to be very cold to make it into a solid. But as you get more and more carbons, after a little while, you can get some other things, okay? So you could get something like, for example, proteins, where there's lots and lots of carbons going on there. Then there's the ionic structures, the ionic kind of solid, and in that case, you know, we know that the positively charged thing and the negatively charged thing, once they're dehydrated, they can form these nice, pretty crystals. And these, of course, are ion-ion attractions. So that's another form of the crystal. So you see that every day in your sodium chloride, for example, although you may not see that it's a crystal unless you look closely, but it is. Then there's another kind of solid that's formed from metals. Now, we didn't really look at metal bonding in this class much, but in general, you know, those metals don't have a lot of extra electrons, and so instead of having electrons that they share between each other, there's this whole sea of electrons here that covers all of these metallic pieces, and there's very strong metallic bonding in that kind of a thing. And so these are the structures of a couple of the different crystals that use metallic bonding. Okay, so this is copper, and this one's magnesium. And the reason they look a little bit different is because of the way they get packed together, which we'll look at briefly in a little while. And of course, metals are really good at being thermal and electrical conductors. They're malleable, which means that you can hammer them into sheets and things like that. And they're ductile, which means that you can spread them out into some kind of a thin wire, for example. Then there's the network covalent. I guess I did label something. Network covalent types of solids, and that would be, for example, carbon. Carbon forms diamond, and carbon forms graphite. And way back when you learned all about energy, you were looking at enthalpy values. And back when, we looked at the enthalpy, and for the graphite, its enthalpy is about 0. And for diamonds, that enthalpy is somewhere around 1.2 or something, and that's kilojoules per mole. So, even though the diamond is very hard and it lasts like for a really long time, in the end, it actually is going to go towards forming that quartz. But that's never mind. Anyway, the network covalent is set up a little bit differently. And for example, here is the graphite. Now, there's a tetrahedral arrangement, and each and every one of these is exactly in line. There's no angle deviation, so they're all 90 degrees and so forth from each other in the tetrahedral arrangement, from molecule to molecule. Or atom to atom, I guess. And then this diamond, it's a little less structured, a little more, well, it's actually much stronger. There's that tetrahedral arrangement in there. And so that's a very, very strong, as you know, a diamond is the hardest substance on Earth. Okay, so let's look at unit cells. So all of these different kinds of solids can be found in characteristic unit cells. We're only really going to think about the cubic unit cell. That's pretty much the easiest one, but there's many other kinds of unit cells. So, I guess I'll go ahead and say this. Lattice is a point in the structure with an identical surrounding, and then the coordination number are the numbers of nearest neighbors, or the numbers that our atoms are going to be touching. Let me see. Yeah. So we have let's look at the crystal lattice. The lattice for a minute. Okay, so we're having a unit cell, and so I usually think of this in terms of a kid's building block, because I can actually draw this all by myself, which is practically a miracle, but also I can see it easily in my head. So this is like a set of building blocks on top of each other, just square building blocks. Now, they show you the lattice point out here, and the lattice point is said to be identical on all sides. But it might be easier if you focus on this piece okay, on this piece, because it's surrounded on all sides by exactly the same thing. All right, so in these cubic units that we're going to look at, we have three possible types of cubic cells. One of them is called the simple cell. We have something called the body center cell, or cubic, and the face center cubic, which we're going to look at all of these in just a minute. I guess we'll just do that right now, actually. Let's look at the simple cube. The simple cube. Okay, so the simple cube has an atom. Notice there's an atom at every one of the points on this, and there's one right there. So it has an atom at every lattice point. Now, in the cube itself, there's only 1/8 of that cube, of that atom. Only 1/8. And I want you to notice that these atoms touch each other along the axis here. So they always touch each other. Now, that's where nearest neighbors come from. And so, in this case, this guy right here in the middle, he's touching this one, and this one, and this one, and this one back here, and this one right here. So it's like a plane. There's 4 blocks where the middle one is touching each and every one of those other blocks and their atom, and then there's the one above and one below. So the coordination number here is 6. It touches 6 things. And because it has 1/8 of an atom at every corner, it has a total of 1 atom in that simple cubic cell. Now here's the body center cubic. And in this case, this has still all of the 1/8 of an atom at every corner, but now it's got an atom right in the center of it. Okay, so in this case, this has 1/8 of an atom at 8 of the corners and the 1 atom at the center. So it has a total of 2 atoms in that cell. Now it has a coordination number of 8. So in this case, if you look at, it's easiest if you look at actually the center cell. And at the center cell, the center atom, you can see that it's touching only 8. It doesn't extend into another cell in any way. So it's contained completely in that cell. So it has a coordination number of 8. Now, I want you to also notice these atoms on the corners don't touch anymore. They're not touching each other anymore. They only do that in the simple cube. Then our last cubic cell is something called the face center cell. Lots and lots of metals get packed into the face center cell. Now, in the face center cell, you still have 1/8 of an atom at every corner. I can't get that last one, but it's still at every corner. Here's 1, 2, 3, 4, 5, 6, 7, 8. Okay. And each one of these is touching the centers, I haven't said what it does. In this case, there are 4 atoms, there's 6 atoms at the face of that block. Half of that atom is inside the block we're looking at, and half of the atom is in the neighboring block. So, in this case, because there are 8 atoms, 1/8 at each corner, and there's a half an atom at the 6 faces, this has a total of 4 atoms in the cubic cell. Now, the coordination number is a little less easy to see. But here's how this works. Let's remember that this face center atom is half in one cell and half in the other. Now what it doesn't do, and what I wish this showed better, is this right here, that atom, doesn't touch the atom on the back side. There's no touching in the center. So that means, though, that we've got, let's do this in a different color for a minute. We're thinking about this atom. It's touching 1, 2, 3, 4 atoms at the corner. It doesn't touch the other atoms at the corner. And then it's touching 1, 2, and then on the inside, on this side, it's touching this third one, and it's touching the one down here. So it's touching 4 faces. It's touching 4 of those atoms. Is that right? Yeah. And then it also is touching in the next, oh, that didn't fall off. It's also touching in the next block another set of atoms. And so the coordination number ends up being 12 here. Now for me, this one's harder to see. But if you'll study that picture in your book, you'll be able to, kind of visualize that, I think. Now, after the cubic cell gets built, okay, then those things get packed together. And so another thing that determines some of the physical and chemical characteristics of how these things work is how they get packed together. So in this case, you have the first layer. And you just put down a bunch of these cubic cells, and you'll see that there's this little diamond shape there. Now, there's two ways you can put in the next set. Okay, the next set, you can lay them right on top of each other. And so you continue to hold that kind of that diamond shape in there. Or, down here, you can put the next cubic cell right over that hole, that diamond-shaped hole. And then the next, of course, would be on top. So you can see sort of that the diamond is right here, but you can't see it anymore because that space is filled in with the second layer. Then, one more complication on packing is the way these things get close packed. And so this is called the hexagonal closest packing, and this one is called the cubic closest packing. In this case, we have some space left between them, and in this case, we don't have any space left between them. Okay, so I guess we just have a couple of examples to go through. And, I wanted to show you this. Okay, so this is X-ray crystallography. And what this is somebody crystallized hemoglobin, okay, which is a technique that's pretty cool and so forth. But anyway, they crystallized it and they shot these X-rays through it. And then they get this kind of this jumbled mass, and each of those dots represents some kind of an atom arrangement. Well, really smart people can take that information and they can figure out what the protein overall structure is. Okay, and then so we actually we know what a protein molecule looks like in a sort of a solid state for hemoglobin because we have these great X-ray and diffraction techniques that can be used to help us see stuff. All right, so a couple of examples. We have lead. It's in a face center cubic cell. And so I want to know how many atoms are in the cell. Well, the face center cube has 1/8 times the 8 at the corners plus 6 times 1/2 at the faces. And so this has a total of 4 atoms. If I ask you what the coordination number is, that's how many it's touching or its nearest neighbors, and that's going to be equal to 12. All right, which of these would crystallize as a molecular solid? So let's look at some of our choices here. We have an ionic thing. So that's not going to crystallize as molecular. Remember, molecular is a covalent kind of molecule. That's also going to let out the aluminum sulfate because that's also an ionic structure. Diamonds are network covalent. Oh, and there's all kinds of cool stuff you can do with this network covalent stuff these days, too. Metallic for the tin. That's going to leave us with our, well, you're going to learn this soon. This is called methanol, which is really rubbing alcohol. At any rate, or it can be used as a gasoline additive. But at any rate, this is covalently bonded. This would be your molecular solid. What other one don't we have up here? How about if we put in krypton? One of my favorites because of Superman, but even though that was kryptonite. But anyway, for krypton, that was going to be an atomic structure. So I think I have one more. Yeah. All right, so iron crystallizes in a body center cube. I want to know what the coordination number of that is. Well, these only touch, the center one right here only touches all 8 of the ones on the lattice point. And so its coordination number is equal to 8 because it's touching each of the 8 atoms at the lattice corner. What about its number of atoms? Well, it has 1/8 times the 8 at the corners again, plus 1 in the center, and so it has a total of 2 atoms. Now, you can do all sorts of really interesting and exciting stuff with crystallography. So maybe someday you'll be interested in that.